Welcome back, everybody. Today we're going to be discussing trigonometric expressions and how to simplify those expressions. The first thing we need to talk about are what are called reciprocal trigonometric identities. Alright, these are important, but these identities cannot be found in your textbook, so it's important to take a look at these notes right here. First one I've got written down here is CSC. That really means cosecant. That's how you'd spell it. And that's a reciprocal identity of sine. Reciprocal, remember, is where you flip the fraction over, so that's why cosecant of x is 1 over sine of x. And likewise over on the right side in the green, I have sine of x equals 1 over cosecant of x. SEC, that stands for secant. And the reciprocal is 1 over cosine. And the last one, COT, stands for cotangent. So you have these 6 reciprocal trig identities. And the important ones to remember, just again, sine is 1 over cosecant, and also cosecant is 1 over sine. Right? That's what's really important to remember about these. One little note I like to remember these all by is that each pair has exactly one co. And what I mean by that is we have cosecant, it goes to sine, and cosine is the goes to secant, and cotangent goes to tangent. None of them are going to have 0 cos, so you can't have sine goes to secant, which can get confusing because you see the S and the S, and cosecant does not go to cosine because that would be 2 cos. So each one has exactly one co. That's really important to remember here. Another identity that we talked about a couple classes ago was the tangent identity, which is where we just say, hey, tangent of x is the same thing as sine of x over cosine of x. And we learned that one from the opposite over adjacent, where the opposite was the y value, the adjacent was the x value, and the sine happened to be the same as the y value, the cosine happened to be the same as the x value. All right, one that Mr. Jolly spoke about last class specifically were the Pythagorean identities. And for the Pythagorean identities, we have this sine squared x plus cosine squared x equals 1. That's something we might remember. I'll highlight that right here for you. All right, but what else we also saw Mr. Jolly do was when he said, well, what happens if we subtract cosine from both sides? So you can get something that looks like sine squared x equals 1 minus cosine squared x. Or maybe if you subtract sine from both sides, you get cosine squared x equals 1 minus sine squared x. So those are 3 different ways to write those Pythagorean identities. Okay. Another thing to keep in mind with Pythagorean identities, we could write it some other ways too. And that's if we take the original sine squared x plus cosine squared x equals 1. And we go ahead and divide by some values. For the first example, let's just divide everything by cosine squared x. And it's an algebraic equation, so you're allowed to divide everything by cosine as long as you keep the equation balanced. So you're dividing all the values by the exact same thing, cosine squared x. And what happens is we get sine squared x over cosine squared x. That's the tangent identity. So it's the same thing as tangent squared x. Cosine squared x plus divided by cosine squared x, that's just 1. And then 1 over cosine squared x, that's a reciprocal. Well, that could be secant squared x. And what happens as a result is now you've got this tangent squared x plus 1 equals secant squared x. And just like what we saw before, we could technically rewrite this. We can subtract tangent squared from both sides, or we could subtract 1 from both sides, and we can write this a couple different ways. So I'm going to go ahead and write those down real quick here. And voila, here's a couple different ways to write those down. You can say tangent squared x equals secant squared x minus 1. That's just by subtracting 1 from both sides. Or you can subtract tangent squared from both sides, and you get 1 equals secant squared x minus tangent squared x. Or the last one is you subtract secant squared from both sides, and you subtract 1 from both sides, and you get tangent squared x minus secant squared x equals negative 1. All right, what we could do as well is we could rewrite this a different way. if we go back to our sine squared x plus cosine squared x equals 1, instead of dividing by cosine squared x, we could technically divide everything by sine squared x, and that's going to create some identities for us as well. Just like we had before, sine squared x divided by sine squared x is going to become a 1. And then we have cosine squared x divided by sine squared x. Well, that's actually cotangent squared x. And the last one, 1 over sine squared x. That's a reciprocal. That is cosecant squared x. And we can do some rearranging, and we can write a few different equations with these values as well. So we're going to do that now. And voila, we have our other equations that could be written. The key for all of these equations, though, goes all the way back to what I highlighted at the very beginning of this Pythagorean identity, right back up here. It's the sine squared x plus cosine squared x equals 1. We can derive all other formulas from that. That's really the key. So if you're ever in a situation where you need to memorize these, just remember the Pythagorean identity, sine squared x plus cosine squared x equals 1, which is like x squared plus y squared equals r squared, where the radius happens to be 1. And then we can derive all the other identities from that. The last ones we have to talk about today are double angle identities. There are 2 double angle identities we're going to focus on today. The first one is sine of 2x, and the second one is going to be, we'll do it in red, cosine of 2x. And so first with sine of 2x, we're not going to go into the proof of this identity. We can prove it using triangles. It's a kind of a long proof. But we're just going to say sine of 2x is the same thing as saying 2 times sine of x times cosine of x. That's how you can rewrite that identity. For cosine of 2x, same thing. We're not going to talk about the y right now. We're just going to talk about this is what it is. It's cosine squared x minus sine squared x. But the cosine could technically be rewritten a couple different ways if we do a substitution method from above, where we say, oh, well, cosine of 2x, you could say, well, cosine squared of x, that's the same thing as 1 minus sine squared of x. So you basically have 1 minus sine squared of x minus another sine squared of x. And that would simplify to 1 minus 2 sine squared of x. And if you did the same thing, except substitute for sine squared of x, you would get another one that says cosine of x is 2 cosine squared of x minus 1. So technically with cosine squared of x, there are 3 different identities you could come up with. For cosine of 2x, I mean, this double angle identity. There's one right there. There's a second one. There's a third one. 3 possible double angle identities for that one. And again, you just need to memorize cosine squared x minus sine squared x, and the other 2 can be derived from the substitution method to find those other identities. All right, now let's take a look at a few examples. So we're going to go ahead and scroll down to the next part of the page. And the name of the game today is simplification. How can we get these things to look a lot more simple than what they currently look like? First problem, cosine of x over sine of x. Well, that's a tangent identity. So that's going to be cotangent of x. That's it. That's what we're trying to do on these particular problems. Okay. For the second problem here, I can see cosine cubed and a cosine. Cubes are usually a red herring for saying, hey, I need to factor out a common term. And in this case, I'm going to need to factor out a cosine of x out of both the first and second term. And what happens is I end up getting cosine squared of x plus sine squared of x. And if I go back up and look at my Pythagorean identity, cosine squared of x plus sine squared of x is the same thing as 1. So this literally just simplifies to cosine of x. That's what we're trying to do. So we just went from something that looked pretty complicated up here to something that actually turned out to be pretty simple. So it simplifies quite nicely. That's kind of the goal of these types of problems. I personally think they're kind of fun to look for those simplification processes, but that's the idea. Let's take a look at a couple more examples here. part C is cosine of x times secant of x. Well, we know what cosine of x is. Secant of x, we can rewrite it as 1 over cosine of x. So that's just really cosine of x times 1 over cosine of x. The other one is cosine of x times, where we get the secant of x, it's cosine of x over 1. So the first one becomes cosine divided by cosine. Those will divide out and becomes a 1. The second one is cosine times cosine. That's cosine squared of x. And we have 1 minus cosine squared of x. Well, that just becomes sine squared of x, and that's what we would get for number 3. We started with this whole weird thing. It simplifies all the way down to sine squared of x. So we're just trying to play with it, figure out how can we get this as simple as possible. And whenever I see inverse trig function or reciprocal trig functions, I really think first and foremost I should try and identify the sine and cosine version of them instead. I think it's a little easier to work with for me. So for example, part D, secant, I can rewrite as 1 over cosine of x. Cotangent, I can rewrite as cosine of x over sine of x. Again, that's just a reciprocal identity. If I go back up here, I can say, hey, well, if tangent of x is sine over cosine, cotangent of x is going to be cosine over sine. And that's where I come up with those values. And now I've got a down here back to part D, I've got cosine divided by cosine. Well, this is 1 over sine of x, and 1 over sine of x is really cosecant of x. That's how we'd simplify part D there, the example there. Okay, let's zoom in on part E. I'm just zooming way in so that way it's easy for me to write small for part E. So again, I have the sine, I have a tangent, and I have a secant. I think the easiest way to deal with this particular problem is going to be, let's try and put it all in terms of sines and cosines first. So I'm going to rewrite secant as 1 over cosine. I'm going to rewrite sine as, or tangent as sine over cosine. Now, I see that I have these cosines in the two problems here. So if I can multiply the numerator by cosine over cosine, which is just 1, I can rewrite this as sine x cosine x over cosine x plus sine x over cosine x. Now I've got a common denominator. Likewise, I can do the exact same thing with the denominator here, multiply the 1 by cosine over cosine. It looks kind of weird right now, but this is really going to help me be able to write these in terms of a single denominator now. So now my numerator, I can rewrite it as sine, I'm going to write it over here, it's going to be sine x cosine x plus sine of x all over cosine of x. The denominator is going to be cosine of x plus 1 all over cosine of x. Well, whenever you're dividing one fraction by another, you guys might remember you can actually multiply by the reciprocal of that. So I can rewrite this numerator as that, all over cosine times cosine of x all over this cosine of x plus 1. And then the cosines will go away. And now I'm just left with this sine x cosine x plus sine x all over cosine x plus 1. It's getting a little bit simpler, but not much. But now I can see a common factor of sine right here that I can factor out. Sine of x times cosine of x plus 1 all over cosine x plus 1. And I've got a cosine x plus 1 divided by cosine x plus 1. That goes away. And this really simplifies out to sine of x. Sorry for the messy work. It kind of worked backwards there. But that's how part E is going to look. All right, last example, we'll go over part F together here. All right, looking at example F here, I'm going to zoom in on this one as well. This one is a double angle identity. I see the cosine of 2x. Well, and I see a cosine squared of x in the denominator, so I know I'm going to want to use cosine somehow. I know I definitely don't want to use that 1 minus 2 sine squared of x identity for the double angle because it won't have a cosine in it. So let's start with the one that I gave you guys first, which was cosine squared x minus sine squared x all over cosine squared x. So we just kind of have to play around with it and see if this one works for us. What the temptation is from a lot of students is they see, oh, cosine squared x divided by cosine squared x, and they just say, let's divide those out, and we get 1 minus sine squared x. Unfortunately, that does not work. We can't do that. What we could do, though, is we could technically rewrite this with common denominators, like break it up into two separate equations, and that might actually help us get to an answer a little better. Cosine squared x over cosine squared x minus sine squared x over cosine squared x. And what happens with the first half, we get cosine divided by cosine. Well, that's just going to make them a 1. Sine squared divided by cosine squared, you might remember that from the tangent identity. Well, that's tangent squared of x. So we've got this thing simplified. We just need to make sure that 1 minus tangent squared of x is that one of our identities from before. I have tangent squared of x plus 1, but not minus 1. So I can't really simplify that anymore. So unfortunately, this is going to be as simple as this one gets. 1 minus tangent squared of x. Okay, now there's 3 practice problems here. I want you guys to give those 3 a shot. And I'm going to pause the video. I'll write down the answers. So go ahead and work on those 3 problems. Give them a shot, and then check your answers here. All right, for the last 3 examples, you have cosine x times tangent of x. Let's rewrite tangent as sine over cosine. And we'll see that those cosines will divide out, and we're left with just sine of x. For example B, the double angle sine of 2x can be rewritten as 2 sine of x cosine of x. And we'll see, hey, there's sine divided by sine, cosine divided by cosine. There's no pluses or minuses, so we don't need to worry about any weird things like that. So you're just left with the 2. And for part C, secant squared x minus tangent squared x, I scroll back up here, and I find that identity. Hey, there's secant squared minus tangent squared. That's just 1. So that's how I end up with that answer there. I hope this video is helpful for you. Go ahead and get it started on the assignment. I have the answer key posted as well. And as always, make sure to hit up office hours if you're confused on something.